Now, one dimension implies that the motion of the particle is in a straight line. That means the particle, it moves in a straight line. Now, say, how do we know that a particle it possesses simple harmonic motion? That means it is moving with simple harmonics in it. We see that, say we find that a body is moving in space or wherever, and we find that it moves in a straight line, and we can mark the starting point as A for our convenience. Then we see that as it moves from A, it goes to a point, and when it reaches this point without a pause, it returns back to A. Again, it goes back and reaches the same point, and it returns back to A, and it keeps on repeating time after time. Now, this point of return, we will call it C. Now, an emotion which starts from a point and it goes to another point and it returns back to the initial point through the same path, right? That means it is following the same path, the straight line. Now it is going to C and is returning to A through the same path. Then this kind of a motion is oscillation. Now, simple harmonic motion is a special form of oscillation. That means not all oscillations are simple harmonic. Okay. Now we will see how will we find that this particular motion which we are observing is simple harmonic or not. Now, first, what we'll have to do is that we will have to time this motion. Now, when we take a stopwatch and start to time it, we see that as the particle moves from A to C and back to A, let's say we have recorded that it has taken t seconds. Okay, and in the next cycle we see that when it goes from A to C and back to A, again it has taken t seconds. Now, after each cycle, that means it covers this entire path from A to C and back to A in equal intervals of time. Now, this time, this t seconds, which is required for the particle to complete one cycle, is called a period. Okay, it's called a time period, period. Okay, and it is denoted by t. Okay, now all oscillations do not possess this property. Well, sometimes the oscillations are such that the time taken by the particle to move from A to C, say if it is t, and or sorry, it goes to from A to C and back to A, and then in the second cycle the time may vary. Now that is indeed an oscillation, but it is not simple harmonic. Now this is one of the very important attribute, the periodicity, for a motion. Now the next feature which is very important in a simple harmonic motion is this. Say for example we divide this entire path from A to C into two equal parts at B, which means that AB is equal to BC. Then we start timing this particular motion as the particle moves from A to C and back to A. Then we find something rather interesting. What we observe is that this particle is not moving with uniform motion. That means its velocity is not constant as it moves from A to B and back to and B to C and back to A. Now B is just an arbitrary point which divides this particular line of motion into two equal parts. That is very important, which is AB equals BC. Now, as we time this motion, we see that as the particle moves from A to B, it speeds up. Its speed increases. Now, the moment it passes B, it moves with decreasing speed. That means its speed it decreases. Now, another interesting thing we observe is that as it moves back from C to A, its speed keeps on increasing, and as soon as it reaches the midpoint, its speed begins to decline as it goes back to A. Now, this keeps on repeating as cycle after cycle. That means as it moves from A to B, its speed increases. And the moment it passes B, its speed begins to decline. It reaches C. Then when it tries to come back to A, its speed also. Well, sorry about that. I forgot to put my mobile phone on silence. Okay, we'll continue. Now, another interesting fact which we will observe is that we need to time it very carefully. That as it moves from A to B, its speed becomes maximum at point B. All right, and as it goes from B to C, as I mentioned earlier, its speed decreases until it becomes zero here. And as it returns from C to B, again at point B, its speed becomes maximum, but in the reverse direction. And this maximum here and this maximum here, they are same, but only in the opposite direction. That means as it moves from A to C, this maximum speed here is equal to the speed here as it goes from C to A. Now, when I say, I'm not using the word velocity because velocity implies direction, but you can say that the speed is magnitude. The speeds are equal. That when if you want to write the equation in velocity, it will be v, let's say A to C, is equal to minus v C to A. That means at point B. Yes, this is the vector diagram. Now this is another interesting observation about simple harmonic motion. But we are going to see what the next point. Well, here comes the final test, the litmus test, which will prove uh, if this motion is a simple harmonic or not, because a simple harmonic motion has to follow this equation, which seems rather complex. Well, we will, as we progress, derive this particular equation, but let us just take a note of this equation, which means that this xt is the displacement of the particle. Okay, now this displacement for convenience is always measured from point B, the midpoint. As it moves from A to C, B is the midpoint. Now this displacement of the particle from the point B, the midpoint, at a given time t is equal to xm. What is xm? Xm is called amplitude. Now xm is actually the distance from A to B, or it is the distance between B to C. Now A to B, as we recall, is equal to BC. Okay, now this xm is the distance A to B, which is equal to BC, of course. Now what this equation is saying, that the displacement of the particle from this point B at a given time t is equal to xm, that is the amplitude, which is also called amplitude, into cos omega t plus this is phi, this is psi, whatever, this is a constant. Now here t is the variable, t, that means x is a function of t, the rest are constant. Well, this omega, this is called angular frequency. Now don't worry if you do not understand these terms, we will derive this equation and we will make these terms clear. But what is this angular frequency? Angular frequency is equal to twice pi by t. Now what is t? T is the time for this particle to cover one cycle.